Hello, Chem 111. I'm going to do a short video on the Spectrochemical Series and how this can affect the spin or the number of unpaired electrons in transition metal compounds. So my first example is going to be an iron compound. It is going to be iron with 6 cyanide ligands around them, that's Cn-1, and the whole thing has a -3 charge. So one of the first things we have to do is figure out on the iron what the charge is on the iron and how many d electrons it has. So since each cyanide is a -1, there are 6 of them, the whole thing's -3, that tells me that it's going to be an iron plus 3. And it's sometimes easier to start with what the electron configuration is of the neutral atoms. So iron has the argon core, and then it would be 4s2, and then 3d, 1, 2, 3, 4, 5, 6. I'm counting on my periodic table. Okay, so to make iron plus 3, I'm going to take away the 4s electrons and one of the 3ds. So iron plus 3 is going to be argon. The 4s electrons are gone, one of the 3ds, so it's going to be 3d5. So this is a d5 metal ion. Okay, and since there are 6 ligands, I know this splits like an octahedral complex. So 3 on the bottom, 2 on the top for the orbitals, right? This is the T2G level, the EG, if you did that in class. Okay, so now I have to think about how do I put the 5 electrons in, and this is where the Spectrochemical Series comes in. I have to know something about the size of this delta O. Is it large or is it small? Because that's going to dictate the way I put the electrons in. If it's a large energy gap, then I'm going to fill the T2G level before I go up to the EG. If it's a small energy gap, then the energy to pair up the electrons is going to be more than moving up to the next level, and so I'll fill them differently. So this is where the Spectrochemical Series comes in, and I'm just going to change the color of my pen here to blue. Spectrochemical Series, I've written it up here at the top. And I've got, it's an abbreviated one of the one I usually write in class. On this side, I have what we call the strong field ligands, and these have a big delta O, and down here are the weak field, right, which is a small delta O ligands. So I have to say what kind of ligand do I have, and I happen to have cyanide, and so Cn-, right, that is a strong field ligand. And so that means that I have a big energy gap, a big delta O. So that means that I'm going to pair the electrons before I would go to the EG level, because the energy to move up to the EG level is more than the cost of pairing those electrons. So I have 5 electrons, and I would fill them in like 1, 2, 3, 4, 5. And so this particular compound, this iron hexacyano compound, would have 1 unpaired electron. And in this case, we would call this low spin because it has lots of paired electrons. So the fact that I'm pairing before I moved up, this would be a strong field, big delta O, and this would go with a low spin situation because I pair the electrons before I move up to the EG level. Okay, my next example is going to be another iron complex. So in this case, and I'll just make sure I have my white pen, we have still iron, and this time, instead of having Cn- as ligands, it has 6 waters, and this has a 3+ charge overall. Since water's a neutral ligand, I know that this is iron plus 3, and on the last slide, I just figured out that its electron configuration is argon 3d5, so it's a d5 ion. So now I have to try to figure out exactly what's going on and what kind of ligand, right? This is an octahedral complex, so I know that I'm going to have a T2G level and an EG level. But again, I need to figure out what is the size of delta O so that I know whether or not I should be pairing electrons first or moving up to the EG level. Okay, if I look, over here is where water is. It's on this weak field end of the Spectrochemical Series. Again, this is an abbreviated one, but water does tend very often to be a weak field ligand. So I'm going to use it as a weak field ligand. So we're going to say water is a weak field ligand. And so that means it has a small delta O. So that means I move up to the EG level before I pair electrons. So I put my 5 electrons in as follows. I would do 1, 2, 3, and then I would go up here to the EG level 4, 5. And so this would actually have 5 unpaired electrons. So this one is very paramagnetic because it has a lot of unpaired electrons, more so than the case that we just did. And this would be called the high spin case because I have more unpaired electrons. So I will just go up here, right? Weak field, small delta zero. This is going to go with high spin. Okay, so those are 2 examples. Okay, my last example is going to be a copper compound. So it's going to be CuCl6 4-. And you may have seen this in one of our prior videos. So if you want to go ahead and try this one on your own, why don't you stop the video now? And then you can resume once you've done the problem. Okay, so the first thing I need to know is about the number of d electrons in that copper. This is a copper 2+. There are 6 chlorine ligands, each one's -1. Overall charge is -4, so that means it's got to be a copper +2. Okay, so thinking about copper, it's one of those exceptions to the electron configuration. It's got the argon core, 4s1, 3d10. So copper +2 is still going to have argon core. It's going to lose the 4s1, one of those 3d electrons, and just be 3d9. So this is a d9 ion. And then I have to think about, okay, my splitting. I have my T2Gs, I have my EG, and I need to know about the size of delta O. So you might notice that the spectrochemical series I had to add on at the end. Cl- is even weaker than the F-. So this is a weak field ligand. So Cl- is weak field, right? Which means it has a small delta O, which means that I'm going to move up to the EG before pairing electrons in the T2G level, right? The energy gap is small, moving up costs less energy than pairing the electrons. And I think for this one, I'll make them green. So let me go ahead and fill in my electrons. I have 9 of them, so I would do 1, 2, 3, 4, 5, 6, 7, 8, and then 9. And so if I wanted to know, for example, how many unpaired electrons, it has 1 unpaired electron. And that's the answer for this one.